Let's analyze the running time of buildheap. So here's a heap, and buildheap calls maxheapify on all of the nodes, or all the nodes except for the leaves if you want to. And maxheapify takes order 1 plus height of the node time. So we have the leaves which have height 0, so those essentially we do not need to call maxheapify. Then we have the nodes of height 1, height 2, and in this example the root has height 3. So the running time is the sum over all nodes and then order 1 of their plus their height. So the order 1 will overall contribute a linear term, because if I have n nodes and everyone contributes a constant, that gives me order n. So the interesting part is the sum over the heights, and we can rewrite those that we look at every height, count the elements, and then those elements get a weight of h in that sum. So I would be looking at, for instance, the nodes of height 0, and they contribute 0. So I would look at the nodes of height 1, where we here have 3 and they contribute 1. The one node of height 2 contributes 2, and the root here contributes 3. So now we have to look at how many elements of a certain height do I have. So half of the nodes are leaves, half of the remaining nodes are of height 1, and so on. So if we write this out, so this is n half, and then essentially n quarter, n eighth, and so on. So this gives me the sum over, so number of elements is now n divided by 2 to the h plus 1. So for the leaves, h is 0, then that's n half, and so on. And now this is multiplied by h, because every node contributes its height. Now I'll take the n out of the sum, then I have n times the sum plus order n. And now I claim, and we'll have a closer look at that in a moment, that this sum that we have here is actually a constant, and then overall buildheap runs in linear time. So let me illustrate why the sum is a constant. So we're looking at the sum h divided by 2 to the h plus 1. So let me write that out, and so for the analysis, this sum actually goes from 1 to log n, but let's for simplicity assume it goes to infinity, so then we just get an even larger number. So that's enough to show that the sum that we're looking at is a constant, if that is constant. So this sum is 1/4, 2/8, 3/16, and so on. So what I can now do, I'll take out a geometric sum starting at 1/4. So what I'm taking out is 1/4 plus 1/8 plus 1/16, and so on. The terms that stay, so the 1/4 is in my geometric sum, but if I look at the 2/8, I used 1/8, but there's 1/8 remaining, then there's 2 divided by 16 remaining, and so on, 3 divided by 32. So the geometric sum that I have here, starting at 1/4, that now evaluates to 1/2. And now I essentially have the same as before, just starting at 1/8. Or you could say it's actually simply half of what we had before. So we could do the same trick. Take out 1/8 plus 1/16, and so on. That will give us 1/4, and we have the remaining part where we could do the same, and so on. So overall what we actually get is something that evaluates to the same as a geometric sum starting at 1/2, so 1/2, 1/4, and so on, and that is actually simply 1, and that is a constant.